Hello everyone, I'm Rahul. So today we'll start working with the Comsol multiphysics. So once you click on Comsol icon, it opens up something like this. So as discussed earlier, you can see the model builder here and the application builder is here. And after that, all the things that we have discussed are there: definition, geometry, material, physics, mesh, study results, and developer things. Okay. So those who have not watched the previous video, which have the introduction of FEM, multiphysics, and the basic introduction of Comsol. So you can go check out those videos. Those might be helpful. But anyway, let's start with this. So first, what I'll do, I'll just go to File and click on New. Okay, so here I'll click on Model Wizard. So I'll select it, simple 2D design. Click on this. Here it will give me an option to add the physics first. So today we are going to make a unit cell SAW gas sensor. So in the example of SAW, surface acoustic wave device, basically we have one piezoelectric substrate. Okay, so this is, for example, lithium niobate. So it's a piezoelectric material which is brittle, and over it what we do, we basically grow the IDTs. So these IDTs are made from metal, say maybe from aluminum or whichever you find convenient, suitable for your application. So these are comb like structures. Okay, and these finger pairs are say 100 or more than that for the wave. So what happens when we supply RF signal to this, due to this external perturbation, one wave start flowing through this. Okay, and if this boundary is reflecting, so this will reflect back. Okay, so that's how it works, like a resonator. So similarly we are going to design a unit cell. So for SAW we use structure mechanics. So I explore this. Once I click on structural mechanics, these options will come. So for SAW acoustic wave, I used to select electromagnetic structure interaction. Okay, so click on this. Again, few more options will pop up. Now, since I'll work with piezoelectricity, I click on this, and finally I get the option piezoelectricity solid. So I select this as a physics. Alright, click on add. So you can see it gets added here. Next step is to see the study. I click on this. So it's a step 3 as per our flowchart. So I click on study, and in this I want to see the eigen frequency. Okay, so I click on this, and later on I can also add other studies if needed. So here you can see added study. So these 3 steps are done. I click on done. Now it will give me the main Comsol window. Alright, so we are here. So main sections are global definitions, component 1, then study, then result. And the component 1 has lot of things. That is one, geometry, where we will make geometry or will import geometry from outside, from CAD tool or ECAD, whatever is your need. Then material property, like we'll set the material for each structure in our design. And then the physics, this is crucial part. So from here we can use the multi-physics. We can incorporate various effects into this. So since I have already selected solid mechanics, electrostatics, because I'll be applying the potential and piezoelectricity, because that lithium niobate which I'll use will have a piezoelectric. So let me show you one diagram. So we'll be making something like this. So if I tell you this is a piezoelectric material, okay, so this is lithium niobate. Over this is PIB layer. Okay, this is for absorption, and yeah, and this one, if I zoom, yes, these are IDTs. These are made from aluminum. Okay, so we are talking about the unit cell here. So we'll make these two IDTs and we'll define the thing accordingly. So in unit cell, this one is piezoelectric material. I shaded it with green. Okay, and the width of this is 4 micrometer, and the height of this is 3 time of width. So this height is 3 time of the width. Okay, and above it is PIB layer. So this we are using for sensing the gas, because we are designing a gas sensor. Okay, so the height of this PIB layer is 0.5 micrometer. Fine. These yellow color boxes are IDT, interdistrict transducer. Okay, so like here I have shown these IDT which are earlier connected to the RF source. So these, if you see the width of this IDT, it's the width of device by 4, so that is 1 micrometer, and the height is somewhere around 0.2 micrometer. Okay, so everything, all the dimensions are mentioned here, which we'll be using in the example which I'm going to simulate just now. So before that, let me start with the tool step by step. All right, and the distance, the dimension of this is mentioned here. The dimension of this and all, everything is mentioned. Okay, so we'll start with this, but before that, actually, I'll add some parameters which I'll be using there. So there are two ways. One is to just directly in geometry. Suppose you can directly assign the, say you are making a rectangular, okay, and you can assign the uh, length and width to it. Okay, another way is to just make name some variable. Just name some variable, say x and y, and further you can use x and y. Okay, and before that you can give them some value. Okay, so I'm going to do that. So I click on parameter. All right, so in parameter, in setting, you go to this option load from file. So if you see one parameter file is there, so I'll attach this file into the description so that you can use it. So what does this have? If I open this, so these parameter got added. So you can see here T underscore PIB F naught width. Okay, so this width is the width of the device, and TPIB is the PIB thickness. So we have assigned it the numbers. The V are the velocity of a relay wave. Okay, so similarly some fixed parameters are also assigned, like Poisson ratio, Young's module, EPIB. Okay, so now directly I'll be able to use these variables instead of their values. Alright, so next step is to create the geometry. For this geometry section, I have made one video specifically. If you want to go to the details of geometry, you can check it out. It will be useful for you. But for now, I'll be focusing on unit cell SAW device. So I'll make the geometry for that. Right. So for that, what I'll do, I'll just change the unit after click on geometry 1, I change the unit to micrometer. Okay, and what I'll do, I'll just right click on geometry, so these options will come. I'll select a rectangle, right? So I'll make the first rectangle, which is piezoelectric. So I'll have to design the width and height here. So my width is width, and the height is 4 times 3 times width plus PIV. Okay. Okay. So coordinates I'm giving 0 0. So let me build this. Click on build selected, and you can click build all objects as well. So it is coming something like this. Okay. Next. All right. After that, what I'll do, I'll be defining the PIV thing. So I click on layer, and the layer one is PIV. Since I've already included that into this structure, so I'll specify it here. And another thing is the layer is the top layer, PIV layer. Okay. So I select the top. I'll remove this bottom one. Okay. Then I again build all of objects. So you can see that partition of PIV. Okay. Next, I'm going to make those IDTs. Okay. So again, I click here. I select the rectangle. Okay, so here I'm giving it name IDT. I can give the name, and I can keep it like this as well. So the width of the IDT is the width by 4. So earlier it was 4 micrometer. So the width, so the device is 4 micrometer. So the width of IDT will be 1 micrometer. Width by 4. Okay, and height I'll keep zero point 0.4 times PIV. Okay, so PIV is basically zero point 0.5 micrometer. So zero point 0.4 of that will be something around 0.2 micrometer. So let's see how it will come. So let me decide these x and y coordinate. So basically x is width by 8. So zero point 0.5 micrometer it will start. It will start from here. Okay. And the y is already on 12. Y is already on 12. And what is that? That is 4 times, sorry, 3 times width. X, Y. So let's see. Yeah, it's on the exact point where I want this to be on. So for the other IDT, I'll copy this. I'll copy this structure here. So for that, what I'll do, I'll just go to the geometry, right click, click on transformation. Transformation is there, and then copy. Select the object which I want to copy. So the object here is R2. One sec. So this one I want to copy. I have selected. It has come down here in input objects. Okay, and I have to provide the positions here. So y will be the same, 3 times width, and now x will be width by 2, so that is 2 micrometer. Okay, so let me build this. Let's see how where it appears. It's not coming. Why it's somewhere else, I guess. So let me see. All okay. It is here. So we don't need to provide with uh, 3 times because we are already on that point. So let me keep it 0. Yeah, now it's on the right point. Now it's in the right location. Okay. So my geometry is done. I'll still say if you want to explore further in geometry, you can watch out the video, the link you can see on the right top. Okay. So next thing is to add the materials. Okay, but before that, as per our flow chart, I'll add some physics into it. So in solid mechanics, we have piezoelectric material 1. I click on this. So it is showing everything as a piezoelectric material, but we know only this one is piezoelectric material. Okay, so this is one. Okay, so I'll what it will remove everything and select this. So one is selected here. So this is piezoelectric material. So I'll be defining all the things. Okay. So next I'll go to electrostatics, and electrostatics effect I want to see in 1 and 2. Okay, so and this is 2. So these two will see the electrostatic. Why? Because the electrical equation are not solved in the aluminum electrode. No, those IDTs are aluminum electrode because they are assumed to be perfect conductors compared to the lithium niobate, this one, and the PIB, this one, and hence we consider them to be equipotential region. Okay, so we keep these two, and we'll also assign the charge conservation, which is important. The charge conservation will happen in domain 1 only. Okay, lithium niobate. So I click on this, so you can see everything is overridden here. So I'll click on charge conservation. So here 3 and 4 are overridden, 3 and 4 are not applicable. So I'll select charge conservation in this only. Okay, in lithium niobate. So rest I'll remove. I'll just remove these things. So this is it. Alright. After that, the physics is done. Next step is to add material. So I click on material. So first I'll be adding the lithium niobate. So right click on this, add blank material. Okay, so these parameter has comes out, but I don't have anything to fill out right now. So what I'll do, so Comsol has provided one PDF in this. These values are mentioned. So all those four boundary, so all those four are selected. What I want this one only. So I'll remove the other one. Okay, everything got removed. So I select this. So these are the few values which I need to fill out. Okay, elasticity, coupling matrix, relative permittivity, density. So I have these already. You can search it out from net, and many references are available. But anyway, I'll add that file in the description for this material content. So lithium niobate, I change the level first. Okay. So these parameters are here. If you see, so these are here. I'll attach this into the description, but for now I'll be copying it and paste it in this. Well, it has come here. Plastic matrix is okay. Next is coupling matrix. So coupling matrix is also checked. Next is relative permittivity. Relative permittivity is also checked in the density for lithium niobate. This. Okay, so everything got checked. So these are the parameters of lithium niobate, which are easily available on the internet. Anyway, I'll be adding it in the description so you can use it further. Alright, so lithium niobate got added. Next is we'll be focusing on the PIB. So PIB also similar thing. Click on this, click on blank material. So this layer is PIB, layer 2 is selected, and now I need these parameters. So again, I have these parameters from internet, and some of these like young modules and poison ratio, these are the standard values. So these I have already included in parameter. If you see Young's module, poison ratio. Okay, so I'll be writing these things directly. So this density is this one, which I have written just now. Okay, so this is the density for PIB. So you can copy paste it directly here. So switch, in our case we have given 0. So only this RHO underscore PIB value will be there. Let's see the parameter. Switch is given 0. Okay. So if you write RHO underscore PIB, that will do the purpose. That will serve the purpose. But for a generic value, I have written it like this. Okay. I made a mistake here. It is showing. See, you can see this color is different. Okay, because it's not a valid value. We have not defined it here. It's PIB. We have defined E underscore PIB. Yeah, now it is fine. You can name it PIB. Done. The next thing here remains with the aluminum electrode. So I click on this material and I can add this from the library. Add material from library, and here you can see. So I click on built-in. Here you can find aluminum easily. Okay, you just click on this. It is here. I need to select where I want to define. So I want to define these in these IDTs. So I zoom it out. Okay, so this is here 3. Okay, not 2, 4, 3 and 4 both are here. So that's it. The material. Next will be like as per the flow chart, will be defining the so material section. For material section also I have made a separate video, which the link you can see at the top. In this I have explained this in details. Okay, so you can check it out if you need it. Next is to add physics. So for physics also I have made a separate video to for regarding the boundary condition and all in detail. All right, so next step is the physics. You can see in the flow chart, next step is physics. So we'll be dealing with the physics now. For that also I have prepared a separate video where I discussed in details. Uh, you can find it out on the I button at the top right top corner, and I also keep that link in the description. Okay, so to explore this in details, you may check it out, where we have discussed many possible boundary condition like reflection, absorbing, and all. Okay, so for now we have solid mechanics and electrostatics. Okay, so from solid mechanics we'll be giving it the periodic condition because these corner edges should be periodic. Okay, they should not reflect, right? So we'll be defining that how we do that. Another thing is fixed constraint. Like the bottom of this, if you see, so it should be fixed. Huh? So it should not reflect anything from here. And another thing is electrostatics. So here, definitely we will deal with the ground and providing it some electrical potential. Okay. So let's begin with the solid mechanics. For that, what I'll do, I'll click on the boundaries and choose fixed constraint. Okay, first I'm going to define the fixed constraint. Okay. So physics toolbar is here. I'll click on this and boundary is there. So I'll click on boundaries and after that fixed constant. So constant in solid mechanics is here. Okay, fixed constant. So in that I have to define the sections. I have to define the boundaries. So which boundaries? I'm making only boundary 2, this one. Okay, so I don't want anything to reflect back from here to top. Okay, so wave will also go like this, the bulk wave kind of thing. All right, so this is done. Next is periodic conditions. So I want these edges to be periodic. Right? So similarly, in boundaries only, I'll select periodic condition. Here it is in connection. Okay, so for that I need to keep 1, 2, 3, 4 edges. So let's do it one by one. 3. 1. Okay. So 1, 3, 16, 17. These are the 1. So this defines periodic condition for the solid mechanics physics. By default, the periodicity type is set to continuity for all dependent variables. Okay. So this part is done. Next is electrostatics. So if you see on the physics, one arrow is coming. So it is showing overridden. So what is overridden? Basically, these were this in free, all the things are defined earlier. But wherever we have redefined, so those got overridden. So if you click on that free, now you can see these little arrow marks on physics constant and periodic condition. Because we have overridden these from here. Okay, so that is the only meaning. You click on this again, it has reached to free. So it's basically an indication. Okay, now electrostatics. So what I'll be doing, first I'll define the ground. Okay, so I'll make one of the IDT as ground and another one is floating. Okay, so let's begin. Maybe I need to zoom it for that purpose. Yeah. All right, so I click on boundaries and choose ground. Okay, so here boundaries. Where is ground? Ground is here. Ground. So this one, I'm this complete identity I'm defining as ground. So 6, 7, 8, 9. Done. Next is floating potential. Other identity, this one will be termed as floating. Click on boundaries and I'll look for floating potential. So here it is, floating potential. Click on this and this electrode I'll be defining as floating potential. Okay, so 11 to 14. Next, we will define the periodic boundary condition for electrostatics physics. Okay, earlier we have defined the periodic boundary condition for solid mechanics. Okay, because that is also important in electrostatics. So again, click on boundary and look for periodic condition. So again, these are the things. So this physics part is done for this acoustic wave. Only this thing is required, right? Piezoelectric effect is already there in that, so no need to do anything in that. Next, you can see is mesh. So we'll do mesh. So mesh is again a very crucial thing. You should take care. You should take this very seriously because it may change results a lot. Like as I discussed rightly in the first video where we discussed about the multi-physics and FEM. So mesh was the basis of all the analysis. It's the type of mesh you give. Based on that, this FEM tool will approximate your solution. Okay, so for mesh, also I have prepared a separate video. You must visit that to understand it in better way. The link is in the I button top right and in the description as well. Okay, so for now, I'll click on mesh and then edge. So you can see a lot of options are there: free triangular, free quad, mapping, edge, boundary layer. So I'm selecting edge here. So it has come size edge 1. The boundary condition which I'll give to it. Let me zoom it out. So 1 and 3. Okay. So 1 and 3. So here I have selected this edge. Okay, this side. Next, I will select the distribution, how the distribution starts from here to the other end. Okay. So for that, right click on edge, click on the distribution and select the boundary 3. Okay, for that. So for that, I'll select boundary 3 because this is related to PIB layer. Okay. So here you can see in distribution you can give the number of elements. Okay, fixed number of elements. So I'm giving it 4 as it was mentioned in the manual. So this meshing is I'm doing as per the manual. So now I want to increase the mesh size along the thickness of piezoelectric substrate. Okay, so for that what I'll do, I'll add the distribution too. Okay, for that again the same process, right click, distribution. So in distribution 2, I'll be selecting boundary 1. Okay, so earlier I have given, so I'm giving distribution different from here. So I'm giving the different distribution for both PIB layer and for piezoelectric edge. Okay, so in this I'll remove 3. So only 1 will be there for this edge. So distribution type, this time we are changing it to predefined. Okay, and the number of elements 25. So see, that's why we have used 2 distribution, because for this we are defining completely different distribution compared to the above edge that belongs to PIB there. And the ratio, again I can type 25. Okay, so like we are good. So we are good to go. We have defined the edge meshing at this edge, and then we have also assigned the distribution to each. Now we can build. So I click on build all. So now I'll be copying edge 1. So for that, so this edge 1 is here. So for that, I will see more operations. In that, copy is there. Copy edge. Okay. So be careful. We are copying the edge. Copy edge. So it has come up here. So select. So we are copying from 1 to 3 to the 16, 17. Okay, so we are copying from here to these edges. Okay, so source boundaries, I'll select 1 and 3. 1, 3. And here, if you see destination boundary, I'll select, not here. So I'll remove this. For this, I'll like deactivate this and activate this. So now if I click here, that particular boundary number will come into this block. 16, 17. So they are getting copied. Okay. So I can build now also, and I can build afterwards. So I'll do step by step build. So the same thing get copied at this edge also. Right. Next is to define type of meshing. So like free quad or free triangular or other options are also there. So I'll choose free quad. Okay, for that. Okay, so here at the domain entry level, I select domain, and after that I'll select the domain. So this is one. I'll not select this. So 2 and 4 I want to select. Okay, so further. So 2 to 4 I'll be selecting. So this is 4, this is 2. Yeah, so this top layer has been selected here. So here it will be free quad type of meshing in this layer. Okay, so build. So you can see the meshing has been done here. It has divided into small sections. And we can also define its size. So right click on free quad, choose the size. So it's similar to this only, like in edge we have. Okay. So element size parameter is here. Not that. So element size is here. So element size, click the custom, and here we will be defining the element size. So maximum element size, I'll be typing here t underscore pib divided by 4. So if you see what is the dimension of t underscore pib, that is 0.5 micrometer. So that dimension is divided by 4. So t underscore pib is 0.5 and we are dividing it with 4. So it will become 0.125. Okay. So build. Now you can see it got refined. So it's very small now compared to the previous one. Okay. So now I'll do the map thing. I'll click on the mapped. Now build all. So everything got meshed. Okay. Next is study. So in study and result, we'll be able to see the output. So we'll be setting up the parametric suite to solve the model with and without the absorbed species on the sensor. Okay, the parameter switch is used to solve the model once without adding the density of DCM and once with the added density of the absorbed DCM in PID. Okay, so in the global parameters, we have defined the switch. Okay, so we'll be using it here and we'll do the parametric sweep. So for that, just click on the study in parametric. So study is here. Click on parametric sweep. So these options has come up. So so here are the options to add the parameter value, and also click on add. Select. So I want to select the switch. Okay, and parameter value is 0. Now we'll be searching the eigen frequency near the estimated resonance frequency. For that, we just click on the eigen frequency. So here in search for the eigen frequencies around. So this one will type f naught. So f naught we have already defined in the global variable. Okay. So it will be search the eigen frequency around this. Okay. So now next step is to compute. So it will take some time. The process is going on. So there you can see. So basically, we are doing the eigen frequency thing. So for that we did the parametric sweep, and we are searching the frequencies around the center frequency. Okay, so we'll be able to see that thing in result. So it has automatically come down to the results, and it is showing one of the result model shape. So you can see the shape got deformed. So that's how it switched. So if we change the eigen frequency, it will further change the its shape. So let me show you that part as well. But before that, so if you see, this is anti-resonant frequency, and it's around 8.4. So it's around like you can see 8.4 into 10 to the power 8. So around around 850 megahertz. Okay. So this is, so if we change these, so its shape will change. Like see, if you click on plot, so that's how it got deformed. So another frequency, it will give me another result. Okay, so you need to analyze all those things. See, okay, it's going in bulk. So it is showing the effect of wave localization near the surface. Okay. So now I'll be plotting the 2D graph also. So in parameter value switch is 1, so I'll choose 0. So if I further explore, so deformation is there. So click here, in deformation, scale, you can see it here. So scale factor, I check this. So it is already selected. So I'll type the scale factor here. So say it's, so for the results I'll be using this PDF. I'll post this PDF in the description so that you can do it in a better way. Now after that, click on plot. So it has got changed. So if you compare it with the previous one, it's quite different. Now if I go to the model shape and I choose another frequency and I plot it out, so it's again changed. Now for electric potential, you just go to the electric potential section. So it is showing the electric potential also. So it will show it for various frequencies how the potential is distributed. So from here you do the coloring and all, as in all the things you can change according to you. So we choose a parametric value as 0. And then plot it. So in electric potential also you can see the distribution at various frequencies. So So you click on the potential, say parametric value, parameter value 0. Now the say frequency, this is one, distribution is another frequency, it is different. So that's how it works, and you can further analyze this as per your requirement. You can also change the result if you want. Suppose you want to see the arrow surface. So it's plotting the arrow surface. Okay. So that's how you can add from here and produce as it as per your requirement. So that's how we do the analysis and everything, and you can further explore it. Okay, so that's it in this tutorial of saw acoustic wave. I hope this is useful for you, and I put a lot of content in the description so you can check it out, and you can also check out the particular videos for particular sections, which also have the links in the description. So thanks for watching.